Hey, what's going on, guys? It's Mr. Sanchez coming at you with another lesson. Today, section 4.1, part 2. Learning targets, analyze the graph of polynomial function. All right, so first we gotta start off with theorem, all right, guys? There's a second half to section 4.1. All right, so theorem. If f is a polynomial function, of degree n, then f has an n at most n minus 1 turning points. All right, what's a turning point, guys? So let's say our graph is like cube, right? That means that it has two turning points at most. So it can turn here and here. So that's all it means. So basically, if your degree is 4, you're gonna have 3 turns. 1, 2, 3. What are turning points? They're basically local max / minimum. Sorry for yawning. No, they're basically local max / minimum. So let's say the degree is 3. I'm gonna go. It's gonna go like that. There's 2 turns. So that's what we mean by the graph. Well, if it has the degree n, then it has n minus 1 turning points. All right, what else? It also says that if the graph of polynomial function has n minus 1 turning points, then the degree of the function is at least n. So basically, you count the turning points and then you go backwards. So let's say it has 2 turning points, then you can assume that the graph is at least n plus n, right? So let's say you count 3 turning points, then you can say the degree is at least 4. That's always going to be true. It's at least 4, which means it's 4 or greater, and we know that because of multiplicity and everything. It could have it could be a higher power, but we'll go into that later. Which of the graphs, this indicates an example, which of the graph below could be the graph of polynomial function? For those that could, so basically for those that could be polynomial functions, this is the real zeros to state that the least degree the polynomial function can have. For those that could not, say why not. So let's look at these graphs here. So you're gonna notice this graph is discontinuous right here at x equals -1. So not a polynomial. So not a poly. So remember, polynomials are smooth, continuous graphs. So this is neither smooth nor continuous. Oh, it is smooth, but not continuous. Therefore, not a polynomial. This next one, you're gonna notice it's smooth and continuous. So this is a polynomial. Oops, that's not the pen. Is a polynomial. And then the minimum degree is going to be 2. So you notice there's a turn here and a turn here. There's 2 turns. So the degree is at least 3. Okay. Let's go on to the next one. The real zeros. I'm trying to state the zeros. The zeros are so this is degree 3, and the zeros are x equal -1, 1, and 2. This is not a polynomial because it has this cusp right here. Remember, it has to be a smooth line. So therefore, not a polynomial. And last but not least, this next one is a polynomial. Right? Again, it's smooth and continuous. It is a polynomial with at least degree with the least degree of 1, 2, 3. So 3 plus 1, so 4. And the zeros are x equals -2 and 1. Okay. All right. So let's move on to the next slide, to the next theorem. All right. And behavior. For large values of x, either positive or negative, the graph of the polynomial function n is f of x equals ax. So basically, for the largest, for any polynomial, right? For any polynomial, if you go to large values of x or negative values of x, and we're talking big, like negative 1 million, positive 1 million, the graph is actually going to resemble the power function of the highest term power. So let's say you have a polynomial x to the fifth minus x cubed plus 3x plus 2. Then your graph is overall towards the end going to look like x to the fifth. All right. The power function of x to the fifth. All right. Let's look at some things called end behavior. So let's see. So basically what we're trying to say with end behavior is the behavior of the graph. All right. So if we have even degrees, you're gonna look somewhat like a parabola no matter what. Yeah, you're gonna have curves and turning points in that parabola, but overall, if you're even degree, you're gonna look like a parabola. And if you're an odd degree, right, odd degree, then you're gonna end up looking like like a x cube, right? All right. Well, we gotta be a little bit more specific. So if we have even degree and a positive leading coefficient, so let's say we have negative 6, positive 6x, then we say this about the end behavior. As x approaches negative infinity, so basically as we go towards the bit smaller values, because negative is smaller, as we go this way, our y values f of x are going to head towards infinity, because the more and more we go to the left, the more and more our graph is going to go to the right, to the top. Similarly, as x approaches infinity, so the more and more we go to the right, the more and the bigger and bigger our y values are going to get. So as x approaches infinity, f of x, our y values are also going to go to infinity. All right. Similarly, as x for even degrees with negative leading coefficients, right? As x goes to negative infinity, so if we head towards the left, then our graph is going to keep going down to negative infinity, right? And as x approaches positive infinity, our y is going to go down to negative infinity. Right. So for even polynomials, the wherever the y values are going is going to be the same for the positive and negative sides of the graph, because it's somewhat symmetrical across the y-axis. I don't know why I'm yawning so much during this video. All right, when we have odd degrees and a positive leading coefficient, the graph is gonna look more like a cubic graph, right? And so basically you can have as x approaches infinity, so the more we go to the right, the higher we're gonna go for a y value. So as x approaches infinity, f of x also approaches infinity. And similarly, as we go more to the left on the function, so as x goes to negative infinity, the steeper our graph is gonna get, the lower it's gonna go, because f of x is gonna also approach negative infinity. And then the opposite becomes true if our leading coefficient is negative and our degree is odd, right? So thus, as we go to negative infinity, we're gonna go to as x goes to negative infinity, you're gonna notice that our y is gonna go to positive infinity. So as we go this way, our graph is gonna go up. And as we go to the left, to the right to positive infinity, our graph is gonna go down to negative infinity. So as x goes to infinity, our f of x equals negative infinity. All right. And now that's everything on end behavior. All right. Now I know this seems like a lot to write down, and it is, but we have a lot more to cover. These are just the first couple of examples. Okay. We're gonna go on to the next slide. All right, and there's just 3 examples left. Some of them are much longer. All right, let's look at the first example up here. It says, which of the graphs could be the graph of f of x where a is greater than 0, b is 0. So this is a polynomial function right here. Right, we're gonna try and determine which one it is. Okay. So we know just by looking at this, though, just by looking at this, you know that the y-intercept is 0, comma, -6. We know that because when all the x's go away, our y-intercept is going to be a constant term, which is -6, which is -6. Okay. We also know it should have the degree is 4, so it should have 3 turning points. And it should open up because our leading coefficient is positive. So just using this information, looking at this, we can tell this one's wrong because it has this one is the graph of a negative in front of the coefficient, a negative coefficient, leading coefficient. We can tell it's not this one because it has 1, 2, 3, 4, 5 turns. Therefore, it's at least degree 6. And now we gotta choose between this one and this one. Well, one that makes this separates this is where our y-intercept is. Our y-intercept should be -6, right? So this here has a positive y-intercept, so it's not this one. So our choice is gonna be the middle one. We're gonna call this one B. Okay. And that's why that's our answer. That's how you can tell which graph is the graph of polynomial. You gotta look at all this information and be able to determine. Right. Next up, we're gonna do something a little bit harder, which is write a polynomial function whose graph is shown. All right, so first, let's list the zeros. So first, list the zeros. So that's x equals -2, 0, and +2. Right. So now let's write that in terms of a polynomial. So that means we're gonna have f of x is equal to x minus the opposite, so x plus 2 times x minus 2. All right. There's always going to be an invisible a here because, well, it's not even invisible. We're always going to have an a there. And I'll tell you why in a bit. All right. So how do we find this degree? So, we have some points here. We'll have this point here. We'll use this one. 2. No, that's not a good one. However, they do give us this point, which is 1, comma 6. -1, comma 6. All right. So we're gonna go ahead and plug that in for x and y values. This is x and this is y. So or f of x, right? So we're gonna have -6. I mean, well, it's +6. So 6 equals to a -1 plus 2 times -1 times -1 minus 2. All right, which is going to equal to a -1 plus 2. It's going to be 1 times -1 times -3 equal to 6. So 6 is going to equal to 3a, which means a is equal to 2. So our polynomial function is going to be f of x is equal to 2 times x plus 2 x minus 2 times x. All right. And we're gonna actually write this down in standard form. So we're gonna have 2 x plus 2 and x minus 2. The difference is squares. So you're gonna have x squared minus 4 times x, and then you can just distribute the x and the 2. So you're gonna have, right over here, we're gonna have 2 x to the power of 3 minus 8x. And that's what our polynomial is going to be equal to. Okay. So if you don't know how to do this, FOIL it out or use the box method. And if you don't know how to get from here to here, just FOIL it out. Just you're gonna multiply some stuff, more steps for me able to do this in my head. So I'm gonna skip that. You can work that out yourself. And all right, guys, just one more thing to go over, and that's analyze the graph of a polynomial function. And we have the 4 steps to analyze the graph. We're going to determine end behavior. We're going to find x and y intercepts, and we're going to determine zeros and their multiplicities, and finally sketch the graph. So how do we determine end behavior? So for step 1, we're going to write in standard form. Okay. So we're going to have f of x is equal to 2x plus 1 times x minus 3 squared, right? So we're going to go ahead and do that. Remember, x minus 3 squared is the same thing as x minus 3 times x minus 3. So you should know that 2x plus 1 times, and then x minus 3 times x minus 3 is going to be x squared minus 6x plus 9. Okay. Which we just gotta distribute one more time. I'm gonna use the box method here because I just think it's gonna make my life easier. All right, so we're gonna just do that. We're gonna have x minus 6x plus 9 over 2x plus 1. So we're gonna have 2x squared. Oh, this is squared, so it's gonna be 2x to the power of 3 minus 12x squared plus 18x, and then plus x squared minus 6x plus 9, which is going to mean that f of x is equal to 2x cubed minus 11x squared plus 12x plus 9. And that's basically it, guys, for our first step. So our degree is going to be power of 3. So our degree is 3 with a positive leading coefficient. Therefore, as x approaches infinity, f of x will approach infinity. Similarly, as x goes to negative infinity, or f of x is equal to negative infinity. Right. Okay. Now we gotta determine the zeros and their multiplicities. All right. Well, find the x and y intercepts. So step 2, finding the x and y intercepts. All right. So for x, they're pretty easy. Right. For x intercepts, you're gonna do 2x plus 1 equal to 0 and x minus 3. Right. So you're gonna put everything in the, well, let me just write the whole thing out so you're less confused. Right. So we're gonna have 2x plus 1 times x minus 3 equal squared equal to 0. So that means you're gonna split this up to 2x plus 1 equal to 0 and x minus 3 equal to 0. So this one means you're gonna get x is equal to negative 1/2. And right here, you're gonna have x is equal to 3. All right, those are x-intercepts. And you plug in 0 for the y-intercept. The y-intercept is going to be 9, right? Because we can actually find our y-intercept from this one. So you're gonna have f of 0 equal to 2 times 0 cubed minus 11 times 0 squared plus 12 times 0 plus 9. So that's gonna go away, go away, go away. So you're gonna get your y-intercept f of 0 equal to negative 9. All right, guys, next up is to determine the multiplicity under zeros. So one thing you notice that this one yields x equals to 1 negative 1/2, and this one yields x equals 3. So determine the zero. So the 0 x equals 1/2 has a multiplicity of 1. And then x equals 3, this should be negative, has a multiplicity of 2. So therefore right here it touches the graph, and right here it crosses. All right, and now lastly, all we need to do is graph this. All right, and let me just all right, so we need some space. So I'm gonna actually graph this in the next page. All right, so we said that our x equals -1/2. It has multiplicity of 1. We said x equals 3 has a multiplicity of 2. And we have a y-intercept, which we said was +9. So when you do your graph, it's actually going to be fairly easy. All right, guys. Not a big deal. So we're going to have 1, 2, -1, -2. So 1. We're going to scale these up a little bit better. Right. And we're going to have this go by 3s. 3, 6, 9, -3, -6. All right, and let's go ahead and mark our intercepts. So 1/2, -1/2 right here. Our y-intercept is 9, and then our x-intercept is 3. Right, so its degree we determined was degree 3. So, and it has a power function of x cubed, right? So it should look like this and behavior wise. Okay. So that means that when we draw our graph, right? So we're gonna cross because it has multiplicity. We're gonna cross at -1, and we're gonna touch here, right? So we're gonna cross at -1/2, which was right here, right? And then you're gonna go to here, and then we're gonna go down, and then we're gonna go back up. All right. Now, this is a sketch, so it's not a best estimate of a graph. However, when you take calculus, you're gonna actually realize we're actually gonna know where the graph is gonna curve, because it can curve here, it can curve in many places. We just don't know where exactly that is. So I just started turning it at 9, but it could turn. The graph could go from here. Oops, sorry. It could go from here to here, or it could keep going higher and higher, higher, all the way up, and then start turning. But for all intents and purposes, we're just gonna guess where it's at. You can use a calculator to try and help you, but we don't have a graphing calculator, so for now we're just gonna sketch our graphs like that. All right, guys. Other than that, that's today's lesson. Have a great day. I will see you all in class. Bye.